Swayam Prabha. Digital India. Educated India.
I welcome you all to the session of thermal engineering basic and applied, and today we shall discuss about the multi-fluid cycle. In particular, we shall do the analysis of this particular cycle to see the efficiency, thermal efficiency, and then we shall discuss the second law of this second law analysis of the steam power cycle. And while discussing, rather while we shall be discussing this particular topic, we shall also discuss the necessity of studying this particular aspect in the context of this module. So, if we try to recall, in the last class we have talked about the multiple fluid cycle, which is also referred as the binary fluid cycle. So, if we try to just before going to see the mathematical analysis in terms of the heat added to the cycle and work which is extracted from the cycle, essentially these components are needed to calculate the thermal efficiency. Now, just for the recapitulation, we have seen that the concept of binary fluid cycle or multiple fluid cycle is coming because of a few shortcomings of the water which is used as the working substance in the previous cycles. So, for brief recapitulation, if we try to recall what are the important qualities of the working substance should have, we have discussed. What are those? High critical temperature, low triple point temperature, high heat transfer characteristics, high enthalpy of vaporization, and finally, low condenser pressure is not allowed. In addition to this, the working substance should not be corrosive, should not be toxic, should be chemically stable and readily available. So, if you now consider water, so it is very difficult to have all these properties in water at the or during the higher temperature part of the cycle. So, if we try to recall, because we cannot change the behavior of water at the high temperature part of the cycle, right, and this aspect allows us to think of different working substances. That means, we cannot reject water as the working substance to be used as the working substance, but we can replace water at the high temperature part of the cycle with more suitable fluids. So, the idea is, if I write, idea is to use binary vapor cycle. So, briefly if we would like to discuss, so water is not used, right, for the So, this is not used for the high temperature part of the cycle. So, it is replaced by more suitable fluids like, so replaced by more suitable fluids like mercury, sodium, potassium, etc. Okay. So, this is, that means we cannot reject water completely as the working substance in the steam power cycle, rather we cannot use water for the high temperature part of the cycle. What we can do, we can replace by this, because you have seen in the last class. Now, what if we try to recall the that means idea is, so you can understand water will be used again in the low temperature part of the cycle, but for the high temperature part we are using either mercury or sodium, or it may be potassium. So, the idea is, so you can see basically in the beginning of this class we have discussed that high critical temperature, properties like high critical temperature, low triple point temperature, high enthalpy of vaporization, high heat transfer characteristics. So, all these properties water is not having at the high temperature part of the cycle, but the same working substance can be used at the low temperature part of the cycle. That means, different fluids are having different attractive features, but not all of them. That means, our objective should be to use both fluids, and that means it is because of this reason, that means different fluids, though these two different fluids are having different attractive features, but not all of them. So, we shall discuss now that in the high temperature part of the cycle mercury will be having a few attractive features, but water will not have. Similarly, at the low temperature part of the cycle water will be having a few attractive features, but mercury may not have. So, it is because of this reason two different vapor cycles operating on two working fluids are combined together, and the concept is binary vapor cycle. So, if we try to write it, so idea is to use binary vapor cycle. If we go to the next slide, if we try to draw the schematic depiction, okay, and then so this is pump, I am giving, so this is a heat exchanger, and this is turbine, and this is condenser. Now, this is, you can see, this is steam water cycle. So, this is the low temperature part of the cycle, because we are using water as the working substance as per our previous discussion. And similarly, the high temperature part of the cycle. So, this is turbine, and this is connected to, right, this is connected to electric motor, Mercury turbine connected to motor. So, we are giving the name Mercury electric motor. This is also the shaft of this turbine is also connected to the shaft of an alternator, and that is steam alternator, we can give the name. Okay. Now, that is again so this is pumped to, this is pumped back to the boiler, which upon receiving heat, so this is the turbine. So, this is, say, this is true. So, this is 1, this is 2, this is 3, this is 4. We can give the name. Similarly, we can give the name, this is 5, this is pump 1, this point is 6, this point is 6, this is 7, and this is 8. So, this is basically Hg cycle. So, you know that this is the binary vapor cycle. Idea was to use both fluids. We are enjoying the attractive features of mercury, which are usable at high temperature. Also, we are exploiting the attractive feature of water at the low temperature part of the cycle. So, this is high temperature part. And this is low temperature part. Okay. So, if we try to draw the TS diagram, so this is 5 to 6, this is 5, this is 6, this is 7, this is 8. And if we try to draw the TS diagram for the TS diagram of the high temperature part of the cycle. So, this is the case. Okay. Now, this is 1 to 2 pumping process. So, this is 1, this is 2, this is 3, and this is 4. So, you try to understand, this is the TS diagram. In fact, we have discussed this in the previous class. In the last class, we had given name, that is mercury so basically it is steam boiler, this heat exchanger is having dual activities. So, you know that this is basically, though it is a heat exchanger, but it is acting like a condenser for the HG cycle, and it is also acting like a boiler for the steam water cycle. So, the heat lost by mercury is equal to the heat gained by the steam or water, not steam water. So, heat lost by the mercury is equal to the heat gained by the water, and that is how water is converted into steam, and finally, it is allowed to expand isentropically in the turbine, and we are getting output. So, you know that design should be in such a way that eventually steam which would be coming at the exit of this heat exchanger is superheated, otherwise the problem associated with turbine blade erosion will be there, that we have discussed extensively when we have discussed about several other cycles. So, now if we go for the discussion and we assume that now in this class our objective should be to analyze, essentially to discuss or to calculate the thermal efficiency. So, if we consider that m kg of mercury is circulated right per kg of steam generation. So, this is what we are assuming. We are assuming that that steam which mercury which is circulated, the mercury which is pumped by this pump P2 to the boiler. So, this is Q in and finally, this is Q out. Virtually there is no heat rejection, I mean in the HG cycle, but there is heat rejection, but that rejected heat is gained by the water. So, effectively there is high temperature part of the reservoir wherein heat is added, and this is the low temperature part of the reservoir wherein heat is rejected. So, if we consider the mass of mercury which is circulated in this cycle is m, and that m kg of mercury is circulated, because mercury would be converted to mercury vapor in the boiler, and then it will go into the turbine for its expansion. And if we consider that per kg of steam, if we need to supply or circulate m kg of mercury, that is what we have assumed. Okay. So, now if we go for the analysis, so analysis of the binary fluid cycle. So, that heat supplied in HG boiler, we are using or this prefix HG to indicate that boiler is associated with the HG cycle. So, this is Q in, and that is what we have seen, that this amount of heat is added to this mercury cycle, and that Q in is equal to m into H HG in, or I can give name HGI. This quantity is basically amount of heat this enthalpy supplied per kg of Hg vapor formed in the boiler. So, if we assume that means m kg of mercury vapor is produced in the boiler, then this is the total amount of heat, right, Q in. And then what is work done? Work done in the Hg cycle equal to Whg equal to mass flow rate into specific work done Whg. So, this is again work done per kg of Hg in the cycle. Right, because we are assuming m kg of Hg. So, this is the total work done. Next is what is the work done in the steam cycle? I am not going to write steam water cycle or the steam cycle. So, this is W steam will be equal to WST 1 into, because we have assumed that for 1 kg of steam generation we need to supply m kg of mercury. So, that is 1 into WST, and this WST is work done per kg of steam in the steam cycle. So, this is essentially per work done per kg of steam in the steam cycle. Okay. So, if we write what is the total work done. So, if we go back to the previous slide, we are getting work output from the mercury turbine, we are also getting work output from the steam turbine. So, the total work output total work output we need to calculate first, and this total work output we are getting at the cost of this heat input Q in. So, from there we can calculate the overall efficiency or total efficiency of the cycle. So, we can write total work output equal to W total equal to m into Whg plus Wst, right. So, overall efficiency. So, overall efficiency of the binary cycle, that is eta overall equal to W total by, so we can write W total divided by Q in. So, we can write this is m into by this is because Q in, that is the expression, right. So, this is the work done for the binary cycle, overall efficiency of the binary cycle. We also can calculate efficiency of the mercury cycle. What is that? Eta mercury, because so this small a small g is used to denote that it is mercury. So, what is eta Hg? So, we are supplying this is the amount of energy which is added to the cycle, and at the cost of that energy we are getting only this much amount of work. WHG. So, this is the expression. So, if we give this equation is 1, this equation is 2, right. So, we have calculated efficiency of the Marconi cycle. Next objective should be, because since we are discussing on the analysis of the binary fluid cycle, till now we have discussed, till now we have calculated the overall efficiency as well as we have calculated the efficiency of the HG cycle, that is the top cycle, topping cycle. So, let me go back to the previous slide. This cycle is also known as topping cycle. So, this is known as topping cycle and this is known as bottoming cycle. Okay. So, our next objective should be to look at the processes of the bottoming cycle and from there we should try to calculate the efficiency or thermal efficiency of this cycle. Okay. So, if we go to the next slide, then that is efficiency of steam cycle. Try to understand, if you would like to calculate efficiency of the steam cycle, we know that what is the work output, right, that is WST, because 1 kg of steam should be generated. So, what is the input energy for that work output? So, that input energy is coming, because in this case you can understand there is no heat source which is supplied externally, rather the temperature of the HG vapor after doing certain amount of work in the HG turbine, when it is taken through this heat exchanger, and while it is passing you can understand that you have studied in even heat transfer course that this is just like counter flow heat exchanger. So, two streams are flowing opposite to each other and at the course of, rather during the course of their flow, because of this heat exchange, the water which is circulated or pumped to the heat exchanger will be heated up and it is designed in such a way that at the exit of the heat exchanger it should be superheated steam. Okay. So, idea is this heat exchanger which is also known as HG condenser and steam boiler. So, this is HG condenser for the HG cycle and steam boiler for the steam cycle, and what we need to calculate that what is the amount of heat that is added to the water, and we have discussed that heat lost by mercury is equal to the heat gain by the steam. So, from there we can calculate the amount of heat added to the steam water cycle. So, if we go to write that, so I am writing heat lost by mercury vapor is equal to the heat gain by water, right. So, if we do like this, then we can write m kg and we do not know the enthalpy of water, enthalpy of HG vapor after doing certain amount of work. So, this is H HG out is equal to H ST, because this is 1, right. So, from there we can know what is m equal to H ST divided by H HG out. Okay. So, what we can write, we can, so this is the expression. So, now the efficiency of mercury cycle, what we had written, that is eta Hg equal to knowing that this is the loss of energy by the mercury during the cycle and that energy should be gained by the water. So, can't we write the expression of efficiency from the perspective of energy balance. So, we know that this is the amount of energy I minus out divided by m Hgi. So, basically this is the amount of energy added to the Hg cycle, but out of this energy we are going to reject this amount of energy to the water. So, this is the net energy that is used to get the work, and that is how the work output from the Mercury turbine. So, this is also the expression, right. So, we can write it. See what is this expression? This expression, if we look at this equation, so m into Hgo is equal to Hst. Why we are doing this? We can write this equal to m H into Hgi minus Hst divided by m into Hgi. Why we are doing this? Because you know that we are going to calculate the thermal efficiency of the steam cycle soon. For that we need to relate this Hst, because that is the amount of energy that is added to the steam water cycle per kg of steam generation. So, if we go one step further, we can write this equal to 1 minus 1 upon m Hst divided by 8 Hgi. So, this is equation number 3. If we now use the expression of m, so this is equation number 3a and this is 3b. So, if we use the expression of m from equation 3a and if we plug in the expression of m over here, then we can write that you know eta Hg equal to 1 minus Hst into m Hg comma I, and that is 1 minus Hst. What is m? M is Hst by Hg. Oh, so I can say this is Hsti, because that is the in. So, this is I, this is I, because so this is the enthalpy of steam at the inlet to the circle, right, inlet to the cycle. So, you can try to understand. So, basically this Hgo enthalpy of mercury, that is Hgo out, is equal to the enthalpy of steam at the inlet to the cycle, that is Hsti. So, that is why I am using this nomenclature Sti. So, if we plug in the value, we can write. So, this is I, this is also I. So, this is Hsti by into Hgi by Hgo. So, we can go one step further, we can write this is 1 minus Hgo divided by Hgi. So, this is the efficiency of the mercury cycle in terms of the enthalpy that we can considered. So, from there we can write the thermal efficiency of the steam cycle. So, efficiency of the steam cycle eta St equal to, what is this? Try to understand. So, this is Hsti. So, per kg of steam, this is the input energy to the cycle, and at the cost of that we are getting work output, that is Wst. So, this is the efficiency that you can understand very easily. So, work output by the heat input. So, energy output by the energy input, right. So, this is the amount of energy added to the steam cycle per kg of steam, and we are getting total work output, that is 1 into Wst. So, this is, we can write Wst divided by Hsti. Okay. So, what is Hsti? Try to understand. HSTI equal to m into HHGO. So, we are trying to express in, so this is m into HHGO and then this is HSTI minus HSTO, because if we look at the steam cycle, so this is HSTI, that is enthalpy per kg of steam which is entering into the cycle or given to the cycle, but there is heat rejection. So, per kg of steam, amount of heat that must be rejected from the cycle, to it must be rejected because we need to run it in a cyclic manner. So, that is Q out is nothing but HSTO per kg of steam. So, and that is, so enthalpy in minus enthalpy out, that is the WST, that is what we are writing. So, if we write it, so this is the efficiency of the steam cycle. So, this fellow is the WST. Okay. So, next objective should be, so basically if you try to recall, we could quantify the efficiency of the binary vapor cycle, we also could establish the efficiency of the Mercalli cycle, finally, we have established the efficiency of the steam cycle. So, our objective should be to see the contribution, rather what fraction of the efficiency, rather what fraction of steam cycle efficiency is contributing the total efficiency of the cycle. So, if you would like to do it, we need to do further calculation. So, if we try to write that overall efficiency, because we need to know the contribution coming from both Mercalli cycle and steam cycle towards the overall efficiency. Is it 60%, 40%, is it 50%, 50%, or it is 30%, 70%. So, overall efficiency, that is eta overall, what we had written, if we go back to the previous slide, that is, this is the expression m WHG plus WST by this. Okay. So, if we write, so that is m WHG plus WST divided by m enthalpy of mercury at the inlet. Okay. So, we can write it, that is WHG divided by HHG comma I plus WST divided by m Hg comma I. What is this? You try to understand, this is efficiency of the Mercalli cycle, because this is the input energy and this is the output work. So, this is basically Mercalli cycle efficiency, right. So, if we go back to this, I mean you can understand that Mercalli cycle efficiency is nothing but this. So, equation 2, m into WHG by m into HGI. So, if you cancel m from both denominator and numerator, you will be getting WHG by HGI. Okay. So, if we go to the next slide, so this is NH, efficiency of Mercalli cycle. What about this term? So, we can try to write it. So, this is WST divided by HSTI. Okay. So, HSTI we can write into HSTI divided by m HHGI. Why you are doing so? So, you know that this is the work output for the input of energy to the steam cycle. So, this is efficiency of the steam cycle, that is what we had written. Let us go back to that. So, this is WST by HSTI. So, to give this expression in the form of steam cycle efficiency and Mercalli cycle efficiency, you are doing this. What about this m? So, this m is, So, we can write it that this eta overall equal to eta Hg plus eta St into H St comma I divided by m Hg comma I. Even it is not in the complete closed form. So, from here also we cannot say what would be the contribution by this steam cycle towards the overall efficiency. So, it is not the closed form, rather what we need to do, we need to again we should try to write this expression in terms of the efficiencies of either steam cycle efficiency or Markowitz cycle efficiency. What about this term? So, if we look at this particular part, so if we look at this particular part now, what about m? So, we can write this is H St I divided by m is already we have calculated what is m? M is H St I by H Hgo. So, equation 3a. So, if we write, so this is H St I into H Hgo into H Hgi. So, if we plug in the value of m from equation 3a, H St I by H Hgo that we are taking in this in the here. So, we can write this is nothing but H Hgo divided by H Hgi. Can you recall? Now, we can write this expression in terms of the efficiencies. If it is not the efficiencies, at least in terms of in terms of efficiency. So, what we can see few minutes back we have calculated this mathematical exercise. So, we can see the expression of H Hgo by H Hgi is nothing but 1 minus eta Hg. So, if we try to write there, so we can write this is eta Hg plus eta St into 1 minus eta Hg. So, this is eta overall. So, this is the final expression of the overall efficiency of the binary cycle, and which is now in the closed form. By looking at this expression, we can at least tell the contribution coming from both the Mercury and steam cycle towards the overall efficiency of the binary cycle. So, this is basically the analysis part of this binary cycle, and it is very easy, just the things we have discussed from our basic concept. So, now finally, I would like to discuss about the second law analysis. So, this is very important, that is second law analysis. See, you have studied about second law of thermodynamics in the context of thermodynamics, basic thermodynamics course, but now question is why do we need to again discuss this particular aspect in the context of the module of steam power cycle. So, we have discussed about starting from the Carnot cycle to ideal Rankine cycle, then Rankine cycle with different modifications, reheat Rankine cycle, regenerative Rankine cycle, and finally binary vapor cycle. So, out of these cycles only the Carnot cycle is the reversible cycle. Carnot cycle, all the processes, if we try to recall, two reversible isothermal processes and two reversible adiabatic processes. So, already I had mentioned reversible. So, all processes are reversible. These are reversible both internally as well as externally. So, so long as the processes are reversible, whether it is internal reversible or external reversible, basically these processes are both internally and externally reversible, there is no need of studying this particular topic. So, basically second law is important, is vital to understand the degree of irreversibility present in any processes. So, this particular analysis again in the context of steam power cycle is important only to know where the irreversibility is, rather sources of irreversibility as well as degree of irreversibility present in any particular process. So, to know that we need to study this particular aspect. As I was mentioning, you know that Carnot cycle is fully reversible cycle, but in addition to this Carnot cycle we have studied about simple ideal Rankine cycle, reheat cycle, and we have seen that these cycles are not reversible. Why? Because these cycles are internally reversible, but these cycles are not externally reversible. Why? Let us briefly draw the schematic. So, this is boiler, this is turbine, this is pump, this is condenser. So, these are the basic components. What we can see that even if we consider the simple Rankine cycle or simple reheat cycle, reheat Rankine cycle or even regenerative cycles, for the regenerative cycles we need to have additional components even for the reheat cycle. But if we consider the simple ideal Rankine cycle, what we can see in this is the schematic which is used to describe the processes in simple ideal Rankine cycle. What we can see, all the processes are internally reversible, right, but what is done over here, heat is added from high temperature thermal reservoir to the boiling liquids. So, addition of heat from high temperature thermal reservoir to boiling liquid, and finally, if we look at this component, so heat is rejected from condensing steam to the low temperature reservoir. So, although processes are internally reversible, but these two processes, that is addition of heat from high temperature thermal reservoir to boiling liquid and rejection of heat from condensing steam to the low temperature part of the reservoir, these two processes are not reversible externally. So, these are highly irreversible process. So, we can't call this cycle as the completely reversible cycle, because though the processes are internally reversible, but these two processes, that is heat addition to the boiler and heat rejection from the condenser, these two processes are externally irreversible. So, if these two processes are externally reversible, we can't call it as a reversible cycle. It is because of this irreversibility, whether it is during heat addition to the boiler or it is during heat rejection from the condenser, some degree of irreversibilities will be there, and so long as the irreversibility is there in any process, it will try to distract the available energy. So, this cycle has the potential to do some work, but that potential to do some work will be destroyed because of this irreversibilities present during in these two processes. So, it is because of this reason we also need to study this second law analysis. Second law analysis will give us a picture about the presence of the irreversibilities, the sources of irreversibilities, as well as it will also help us to measure the degree of irreversibility present in any processes. Okay. So, let us quickly do it. That exergy destruction, that term you have studied in thermodynamics. What do we mean by that? That is resource degradation. Exergy destruction is nothing but the resource degradation. That means these two processes like heat transfer from high temperature thermal reservoir to the boiling liquid and heat rejection from condensing steam to the low temperature thermal reservoir, these two processes will distract the energy at which this cycle will work. So, had these two processes are I mean if we somehow can remove these two processes, if we can somehow ensure that that amount of heat should be added to the boiler without inviting any irreversibility, if we can ensure that this amount of heat must be rejected from the system to the surroundings without inviting any thermodynamic irreversibility, perhaps the efficiency of the cycle would have been better as compared to the case where these two processes will invite irreversibility, and that is the real process. So, that means these two processes are not allowing the system to operate at the best exergetic efficiency. So, exergetic efficiency will be destroyed only because of the irreversibility is present. So, this exergy destruction is the measure of the deviation of the exergetic efficiency of any particular system. So, exergy destruction X destruction dot is nothing but T naught into S dot gen. So, this is the entropy generation. So, basically you know that these two processes will invite, or it will, these two processes will lead to the generation of entropy, and it is because of this entropy generation there will be resource degradation, that is the available energy would be degraded, and as a result of which exergetic efficiency will be reduced. So, this is the equation, probably you have studied in thermodynamics, I am not going to derive it. So, if it is, so this is the expression of exergy destruction for a steady flow system. So, this is the exergy destruction for a steady flow system, right. Let me discuss about one particular case. Say if we consider one system and this is the system boundary. So, this is exergy in, right, I am writing exergy in, this is exergy out, right, and this is basically the system. The system will be having exergy of the system plus exergy destruction. So, if exergy, this is the expression of exergy into the system and this is the expression of exergy out from the system, then we can do this, we can write this, that exergy in equal to change in exergy of the system plus exergy out plus exergy destruction. So, you can understand this exergy in is equal to this exergy in which is added to the system will change the exergy of the system, there will be some amount of exergy destruction plus some amount of exergy that will come out from the system, right. So, if we have multiple inlet, such multiple inlet to the system and multiple exit from the system, we are giving this. So, no matter some amount of exergy destruction will be there and this exergy destruction will be 0 if the process is reversible, okay. But it is greater than 0 for the irreversible processes. That means, for all the irreversible processes this exergy destruction is greater than equal to 0. Okay. So, if we try to write it now, this is the expression in the context of steam power cycle, that is our focus today. So, basically if we can write that x dot destruction. So, x dot destruction is equal to T naught S dot gen. This T naught is the reference temperature. So, this is the reference temperature T naught, let me write it. So, this is surroundings and this refers to reference. Okay. So, what we can write? We can write now this is for the steady flow system for the in the context of steam power cycles. Say if we consider simple ideal Rankine cycle, what we can write? T naught. So, that is m dot S out plus q dot out by T, this is boundary out minus m dot S in plus q dot in by T boundary in. So, this is the expression. So, you know that, so this is exergy in plus, so let me write it. So, this is for the, if we consider, so this is basically what we are writing, this is T naught into S dot out minus S dot in. Okay. So, this is for the steady state steady flow processes. Okay. System, rather I will write system, not process. So, this is system. If we consider that we have single inlet, single exit and per unit mass flow, mass of the working substance. Okay. So, we can write this exergy destruction equal to T naught S exit minus S inlet plus Q exit by T B boundary exit minus Q in by T boundary in. So, basically you know that heat is added to the system, Q in, heat is rejected from the system, whether heat is rejected or heat is added, it is added or rejected through the system boundary. So, these are the temperature of this boundary through which heat transfer takes place. So, T boundary E, that is the boundary temperature at the exit through which heat is rejected. This is the temperature of the boundary at which heat is added to the system. So, now this is for the single inlet, single exit and per unit mass of the working substance. If we would like to write this is for a cycle. So, for the cycle, because if we try to go back, So, this is the cyclic process. It is not that we are focusing only in the boiler, it is not a case that we are focusing only in the turbine. If you would like to focus in the boiler turbine, that you have studied, but we are focusing on the cycle. So, if we try to write this expression, you can write even for all the individual components, but if you would like to write this for the cycle, then it can be written exergy destruction is equal to T naught into Q exit by T boundary exit minus Q in by T boundary in, right. So, this is the surrounding state. Surrounding state. So, now basically if you would like to discuss that what we have written. So, this is for the cycle. This expression you can apply for all the components which are there in the cycle. What we can see from the final expression. So, this is the final expression. I am making a box over here. So, this is x dot. What we can see from this expression, pertaining to this cycle, all the processes are getting executed in a cyclic manner. Some amount of irreversibility is there, and that irreversibility will destroy the exergetic efficiency. What are the sources of this, of the irreversibility? One is, you can see that heat rejection, that is Q exit, and another is Q in. So, basically if we have, if we can figure out the sources of irreversibility, then we also can calculate the degree of irreversibility that is present. So, pertaining to this cycle, as I told you in the beginning, that although all the processes are internally reversible, but only problem is that addition of heat from high temperature thermal reservoir to the boiling liquid, that is this fellow, and rejection of heat from condensing steam to the low temperature reservoir, that is this fellow. So, these two factors are responsible to invite some degree of irreversibilities, which in turn will reduce the system performance by destroying the exergetic efficiency. If you supply, rather if you apply this equation, if you supply certain amount of, if I go to the previous slide, if you supply certain amount of heat to be rejected from the turbine, even some degree of irreversibility will be there. In practice, in real application, that is there, but the we are allowing the turbine surface to be insulated, so that loss of energy from the turbine, the flowing steam to the surroundings is neglected. So, you can understand, if we apply this equation even for the turbine and for the pump, so these two are 0, because there is no heat interaction between system and surroundings. So, this is applied for any module which are there in the steam power cycle, but this is SE minus SI. So, basically when steam is entering into the turbine and steam is leaving, so entropy transport associated with the flow of steam and entropy rejection associated with the flow steam rejection. So, if it is, so long as the process is cyclic, then perhaps the contribution from this term will not be there, and that is how we could write the expression of exergy destruction for the cycle is like this. And having established this expression, we also could identify the sources of irreversibility in the context of steam power cycle, is the heat addition to the boiler and heat rejection from the condenser. So, with this I stop here today, and we shall continue our discussion in the next class. Thank you.